Hi guys, let's solve the problem 3-sum. This is an extension of the problem 2-sum that we've done before. It's more similar to actually the problem 2-sum 2, which we have not done yet, but the problem provides this array of -1, 0, 1, -1, -4, and we have to find three numbers in the array list of all those three numbers where the sum of those three numbers equals to 0. So given an integer array nums, return all triplets, which is all these three values, such that where no index is the same. So basically in the resultant values, I and j and k indices cannot be equal, but the summation of all of them should be equal to 0. And then not only should this not be, not only the indexes should be not equal, but also the solution should not have any duplicates or duplicate triplets. So how should one go about it? The first solution that comes to mind is one can run a nested loop here, meaning an outer loop here saying -1, and then an inner loop, and then a third loop. And the third loop, so the first loop starts here, the second loop starts here, the third loop starts here, but goes on until here. And then if we find a value, we put it. Otherwise, in the next iteration, the second loop moves from here to here. So the first one remains here, the second one starts from here, the third one runs from here to here. And so that's an n-cube solution because there are three loops. Now, there are a couple of problems with that. First, the complexity is n cubed, so the question is, can we do better? And second, the problem is that there could be repetition, there could be duplicates, meaning this is a random list, right? It's not sorted. So there could be a situation where this value, for example, occurs here, but in theory, there could be a combination of values here that neutralizes this value. So we could have a triplet starting this value and those values here, but we could also have a triplet this and those values. So because of these two problems, we'll have to find another solution. So let's give it a thought. Would, if we sort it, would that be helpful? Uh, because sorting is n log n, and we had a solution that was n cubed. So if we can sort, it's almost nothing compared to an n cube solution. So let's say we assume we sorted the list in n log n time, and then what we can do is, if we were to sort this list, it would look something like this: -1, -1, 0. Actually, there's a -4 here as well. -4, and then 1 and 2. So is that beneficial? Well, it may be, because if we start with this one, -4, and then what does the question reduce to? The question reduces to, can we find an offset 4? So if we find -4, and uh, if we can find a 4 here, then we have our triplet. So how can we find a 4 here? We can think of a two-pointer solution, because there are only two ways to do it. One is we run a nested double loop, in which case this is going to be an n square thing. But why do we need to run a nested double loop when in fact what we can do is use a two-pointer solution, which will first will take this value and will take this value. So the summation of these two is, so not only the summation of these two, but we'll have to do the summation of these three. So -4 plus -1 plus 2. So what is that? That is -3. So the sum is less than 0. What does that mean? That means we have to increase the sum. So will we move our left pointer or right pointer? We'll move our left pointer and we'll go here. Well, it didn't change materially, so we'll have to move further. So this is 0, this is 1, but we'll see that none of them actually add to 0, because this is the last. What we can do is -4 plus 1 plus 2, so that's a -1. But then we cannot move L further, because L is will no longer be less than R. So the loop will exit there. But we have only seen our first value. Now we'll have to go on to the second one. So in this particular case, the first value is -1. The value next to it is the left pointer, which is -1, and this is the right pointer. So if we add all these three, what does that become? That becomes 0. So this is one of the solutions: -1, -1, 2. uh, and what would we do if this is 0? So well, if this is 0, what we can do is we can move this number 1 forward, left, or we can move, or the big point is, or we can move right one leftward. So why is it that we don't have to move the both numbers simultaneously? Because if we are here and if we move L by 1, then if the value changes, and we have to make sure that this value is not the same as this, because we cannot be having duplicates. So unless this is not the same as this, we'll keep moving forward. But once we stumble upon a value where it is different than this, then what will happen is, because the summation of the prior value led to 0, right will be forced to move to the left. So that's fine and good, but what is the complexity of the solution? Well, we sorted it. The sorting took n log n time, and then we took one number, we went through the two pointer solution. So this is of order n. So we are going through the entire list n times, and each time we are going through the list again with the two pointer solution. So it's an O(n) square solution. N square is more than n log n, so n log n is of no consequence, but the ultimate complexity is n square, which is better than n cube. Plus the additional benefit of, because it's sorted, we can continue moving our pointers until it is no longer same as the previous value, so we'll avoid the duplicates. Now the duplicates could have been removed in the nested solution as well, because even if we got the duplicates in the first place, we could have sorted the result itself, and then we could have appended only unique results or unique lists. But that is more code than is required, because here we'll just remove it at the outset. So we've discussed all the approach. Let's code. So so define a result. This would be an array, and within this array there would be more lists inside. And then let's sort it. So nums dot sort. Now this will sort it in ascending order. And now here we do need, so it would be very helpful if we not only have the number itself but the index as well, because we are using I, j, and k, and we call it nums of I, nums of j, nums of k. So let's get the index as well. One easy way to get the index as well as the element itself is enumerate. So that's what we'll do. So for I comma n, and nums, not nums actually, this time it would be enumerate nums. So I is the index and n is the value. Now the thing is, in the first iteration I is 0, so that is fine. But in the following iterations, when I is 1, what we have to do is we have to ensure that the second number is not the same as the first number, because otherwise it can result in a duplicate. So let's just take care of that, and we'll say if I is greater than 0, so meaning not in the first iteration but the second iteration, and this number itself is equal to nums of I minus 1. What does this mean? Meaning the second number that we are looking at, in this case 0, is equal to the number that was just preceded. So if this is equal, then what we'll have to do is we'll have to do continue, because we don't want that. We've already considered that. So that's just to remove the duplicates. But now that we've established in the first iteration, let's think we are in the first iteration. So what is L, the left pointer? Well, L is, so we have to define L and R. So let me just write the both of them down. So L would be the next one, because our first integer is at index I. So L is the next one, and R would be what? R would be the length of nums minus 1. So this would be, so this is a conventional two pointer solution, nothing unique about it. So while L is less than R, and that's true, so we are looking at the inner loop. And what is the threesum? Threesum is the combination of n, which was the first value, plus nums of L, which is the left pointer in the inner loop, plus nums of right. And then, as we discussed, if this threesum is, if this is greater than 0, then that means that we have to reduce it. So to reduce it, what we will have to do, we'll have to reduce the highest value, because R is on the higher side. So we'll have to reduce the highest value. Else if let me move it here. Else if threesum is less than 0, then what does that mean? That means that we'll have to increment our left pointer, which we are doing here. Else, now what is else? If it's neither greater nor less, then that means it's equal. Then that means that is one of our results. So we'll append, and what will we append? We'll append a list, and in the list we have to append the numbers, not the indices. But see here, it says we have to provide the triplets with in this fashion. So what we'll do is we already have n, so we'll have to add n, and then nums of L, and then nums of R. So we appended it all, but it does not end here, because just because one outer element, and let's say this element, is there another example? So in this particular instance, they've given examples that are um, okay, yeah, because we sorted it. So let me maybe just r- comment real quick on this example. What I'm trying to say: -4, -1, -1, 0, 1, and 2. So this was the sorted array. So let's start from here instead of here, because we already sorted it. But what we are saying is, for -4 we went through the inner loop, and it didn't bear out, but then we moved the outer element to -1, and then we found a solution, because we started the left pointer here and we've started the right pointer here. Well, initially it did not, it matched in the first go, -1 plus -1 plus 2, so that equated to fine. But just because we found a solution does not mean we do not carry the search further, because we still can find more unique solutions, because in this case we do. We increase the left pointer, this becomes 0, and then the right pointer becomes 1. So this is what we have to be mindful of. So what will we do? We'll say L plus is equal to 1, so we increase L by 1. But is that enough? Now this is where we spoke in the past, and this is an easy point to miss. We cannot just rely on this, because it might happen that this this value, instead of 0, it could have been -1, so it could have been the same as this value, and we do not want that, because if we use that value, we run the risk of getting duplicates. So what we'll do is, we'll say while nums of L is the same as nums of L minus 1, while that is true, we have to continue in incrementing L, meaning we only want unique L if it is available, and it is less than R, of course, which is being governed by here. But now we do not have to change the pointer R. And why is that? Because we know that we've distinctly changed L. The n number n remains same. We have distinctly changed L. So if at all the combination of these three will result in a 0, then that will force R to change. So we do not have to mention that explicitly. But so this is it. This will run the inner loop, and then will the outer loop will continue moving here because of this for loop, and then we can give the result, return the result. Let's run this. Got a runtime error here.
That this is pretty complicated. I'm not gonna.
It says out of range. We have to make sure this is less than R here. And it submits all right. So yeah, this is the ThreeSum solution. It's very similar to the TwoSum 2 solution with those 2 pointers. The additional caveat is we have to sort it. We have to have an outer incrementer as well. And I think the most difficult thing to get to is that we have to make sure that we are not using duplicates. So that would be it. See you in the next one.